Good morning.
I gotta say, on your quiz, I was so thrown off when you said draw the structure for, I forgot what it was. I spent the longest time trying to figure out, we've been doing line angle structures for so long. I was thinking that's what you meant. And I was like, how do I draw a line, start drawing lines in the box?
And then you saw the answer
Yeah. And I
and
think
thought you made it too complicated.
yeah.
Yeah, I wasn't trying to trick people. You can draw it in the box too. I mean, it's just, you got to treat each one as a line. So that's, it's not too bad given the exams in Canvas, but there's some things that it's really difficult to do. And like this last quiz and this test coming up are ones that are really hard to do in Canvas. So that's where I wish we were in person. Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the slide?
Yes.
Thanks. So today's the last lecture of the semester for Gen Chem 2. So congratulations, you made it this far. Thanks for sticking with me through it all. And I know it's been a long year of chemistry stuff, and I appreciate you sticking with me and moving through. I think in general, people have done pretty well, so that's good. There's just a couple more things to do in the semester, so try and finish strong. Today, we're going to talk about nuclear chemistry a little bit, just kind of go over some of the terminology and kind of what it means. And then on Thursday of this week, we'll have our exam number 5, which will cover this chapter 21, and then it'll cover chapter 24, which we had the quiz on the other day. I don't plan on going over the quiz because the answers are posted and it's pretty much either you got it right or you didn't. And I think if you look at the answer, then you'll see what it is. If someone does have a question, I'd be glad to try and answer it. You can ask it live during class, or you can send me a message or something. Either way is fine. So Thursday, it'll be an online Canvas exam, and it'll cover, as I said, the nuclear chemistry stuff, chapter 21, and then chapter 24 that we had the quiz on the other day. I do want to remind everyone that the final exam for this section is scheduled for Thursday, May 6th from 8 to 10 a.m. and that will be online on Canvas. So log on in that time period and take the final exam. Just to remind everyone that, so Thursday we'll take that last exam. I will then go in and I will drop your low exam and I will drop your low quiz. If for some reason you missed an exam or a quiz, that counts as your low one, and that'll be the one that gets dropped. So Canvas has the grades in there, but it has all of them. And so the final percent that you see in there may not be exactly what you have. You have to go in and drop that low one, and I just do that manually. You cannot drop final. So if the final is not one of the choices for the drop exam. It's one of those 5 exams during the year that you can drop. You can't drop the final. In terms of what the final looks like, it'll be similar to one of the exams in terms of length. So it's not like the final is twice as long as an exam or anything like that. It'll be similar in length to what one of the regular exams is. It is comprehensive. It does cover the whole semester. So be sure and go back and look at some of the stuff we did earlier in the semester to refresh your memory. The stuff we've been doing lately is probably pretty fresh in your mind. So you should hopefully remember that. But some of the early stuff, it's been a while since we did that. So you may have forgotten some of that. So any questions on any of that stuff?
Is it worth 100 points?
It is, yeah. I think that's right. I'd have to check the syllabus again, but I think it is. Okay, so let's talk a little bit about nuclear chemistry. It's interesting because when you kind of get towards the end of the second semester, there's options on what you can cover. And originally, I wasn't going to do the nuclear chemistry chapter. I was going to do something else. And in talking to some different people, I heard that some people are interested in nuclear chemistry and kind of curious about it. I personally am not one of those people, but I think it is interesting to just kind of understand a little bit about what people talk about with nuclear chemistry. And so this is just meant to kind of give you a little bit of information around it. There's additional information in the book if you want. But this will at least get you a little familiar with some of the terminology in that. So that's what we're going to do today, is just kind of go through some of this. So when we talk about nuclear chemistry, one of the things we want to get out of the way in the beginning is just kind of the way it's represented. And so hopefully this looks familiar to you, where we have our chemical symbol. In this case, it's carbon. And so you'll have that symbol for whatever atom, whatever element it is. And then the number on top is the mass number. And the number on the bottom is the atomic number. So that's stuff that we've talked about before. That's exactly the same as it was before. Just kind of refreshing your memory on what that is. And so the mass number, remember, mass is the sum of protons and neutrons. So that's where the weight comes from. And then the atomic number is the number of protons. Since it's neutral, the atom is neutral, that's also the number of electrons. So mass number, the one on top, that's protons plus neutrons. The atomic number, the one on the bottom, that's the number of protons, or you can think of it as the number of electrons because it's a neutral atom. So a term that I don't think we've used before is that when we talk about the nucleus, we say it's composed of the 2 nucleons. And the nucleons are represented by the protons and the neutrons. we've talked about isotopes in the past a little bit, and where isotopes come into play is that not all the atoms associated with a particular element have the same mass. And that's because you have different numbers of neutrons in those. So remember, we said here that, and for the carbon, for instance, the 12 number, that's the mass number. That's the number of protons and neutrons. So what that means is that number for carbon isn't always 12, because if you have more neutrons, for instance, then that's where you get, if you have one more neutron, then that's where you get carbon 13, for instance. You may have heard of that. That's where they do the time dating stuff and things like that. And there's areas of chemistry outside of this that you really take advantage of isotopes when you do analyses. And so those isotopic ratios are known, and you can look them up if you want to. When we've been talking, we really haven't focused on the isotopes, but the isotopes are a big deal when we start talking about nuclear chemistry. And here's some examples of 3 isotopes for uranium. So if you look at uranium normally, it says 238, right? Well, there's some other values that naturally occur, and that's based on the number of neutrons being different in those other isotopes. So isotope, that's a term you should be familiar with. You should understand that isotope means basically different numbers of neutrons. So when we're talking about nuclear chemistry, what's really different about that is we're focused now on the nucleus, okay? So you think about all the stuff we've been talking about all year. When we talk about bonds and things like that, we're always talking about those outer shell electrons and things like that. We really haven't talked about the nucleus at all, other than maybe the number of neutrons and protons and things like that. But we haven't done any chemistry in the nucleus. And so with nuclear chemistry, that's the big difference, is now you're looking at what's going on in the nucleus. And so one of the things that happens with some nuclei is that they can change spontaneously and emit radiation. And because they emit that radiation, that's where the term radioactive comes from. And so once again, radioactivity has to do with the nuclei changing and emitting that radiation. Okay, so that's different than, like I said, than the kind of stuff we've been talking about really all year. And so compounds that do that are called radionuclides. So those radionuclides can decay in several different ways to form a different nuclide. And so we're going to be writing some nuclear equations to show how these nuclear reactions occur. So what you'll see when we start looking at the nuclear equations, it's really pretty similar to kind of when we were balancing equations, whether it be the redox stuff or the regular balancing of equations. And so it's just, we're balancing different things. In this case, we're balancing stuff going on in the nucleus rather than balancing molecules. But it's really kind of the same idea. And so some of the things that hopefully you got used to doing in balancing those equations, and the biggest one is paying attention to, is it a plus sign or minus sign, adding things up correctly and writing them out correctly. Some of those skills that you've picked up will really pay dividends here when we do the nuclear equation balancing as well. So, as I said in previously, for chemical equations, we balance atoms and charges, okay? In the nuclear ones, it's atomic number and the mass number need to balance. And so this is kind of like doing these balancing on an atomic scale. And so just to remind you again, what we're saying here is the mass number, the 12, the atomic number, the 6, those numbers on these different elements, those are the numbers we're going to be balancing essentially, okay? So before we were worried about how many carbon atoms maybe, or what's the charge on that. We're not going to be worried about that now. We're going to be worried about that mass number and that atomic number. And we'll be balancing those out. So get rid of this here. So I always like to point out something to you that I think is really important and you want to spend a little time focusing on. And this table that has some of the types of radiation is one of those things. And so here, we're talking about alpha, beta, and gamma radiation. And these are the most common types of radiation that are emitted. And they have some different properties that it's important that you know. So the top row here, we have the symbols for alpha, beta, and gamma, okay? On the left-hand side of the table, in that first column, we have the properties. We have charge, mass, relative penetrating power, and then the nature of the radiation. So what I'd like to do is just kind of go through this a little bit so we can see that. And let's take a look at charge first. We see with the alpha, it's +2, beta is -1, and gamma is 0. And we'll get to it a little bit here later when we go into a little more detail on this of why they are what they are. But for now, it's important that you know those, because this +2 and this -1 are going to be important when you try and balance these nuclear equations. So remembering if it's an alpha or a beta or a gamma, what charge is associated with it factors into how you balance. The mass is fine. We're not going to spend too much time on that, but the penetrating power and this relative penetrating power, all this means is the bigger the number, the more penetrating power it has. It's not saying that's the absolute number. It's just saying comparing these types of radiation, gamma is 10,000 times more penetrating than alpha. And so this penetrating power is a big deal. So the penetrating power is a big deal because I think, as most people probably know, there are some medical applications for nuclear type medicine. And so if you're trying to get a lot of penetrating in, then you would use something that's a gamma emitter. If you don't want much penetrating power, then you'd use an alpha or beta. And so different types of radiation have different uses. So it's important to remember gamma is the most penetrating, alpha is the least penetrating. And then finally, what's the nature of the radiation? So the alpha, we say that's 4 and 2, which is basically a helium nuclei. Beta is electrons, okay, and that makes sense because it's got a minus charge. And gamma, though, that's just high energy photons. So real different in terms of the nature of the radiation of what each of those are. And because of that, and you think about it, you think about a photon versus a nuclei, that kind of makes sense then that gamma is going to be higher penetrating than the alpha. And then the electron in between is kind of in between. So a lot of this stuff in this table, real important, especially when we try and understand the different types of radiation, and then when we go to balance nuclear equations. So let's take a look at these a little more closely. So we mentioned alpha and beta, those are decay processes. Gamma is an emission. There's also something called positron emission and electron capture. And we'll talk about those as well. So when we talk about balancing things, and so here we have the alpha emission, the beta emission, the positron emission, and the electron capture. Couple things in this table. Another one that's real important to you to learn is we're going to hold off on the nuclear equation for a moment. I want to talk about the charge and the atomic, whether the change in the atomic number and the change in the mass number first. So for alpha emission, you have a -2 change in the atomic number. So in other words, that atomic number decreases by 2, and you have a change in the mass number of 4. So it loses a value of 4 there. So remember, mass number was the one on top, atomic number is the one on bottom. So when you have something going on, and that's where this nuclear equation then comes into, we see if we had some element X with a, excuse me, mass number of A and an atomic number of Z, if it has that alpha emission, remember we said alpha is this helium 4, 2, we'd subtract 4 and subtract 2. So 4 from the change in mass number and 2 from the atomic number. So what this element Y that's designated here means is it's two atomic numbers lower than whatever X is. So if X was 10, then the Y would be 8. And it would be that different element. Same idea here with beta. In that case, you have +1 change in the atomic number. The mass number doesn't change. So we see over here on the left, we see now, once again with our X value going to adding 1 to the Z value. And so then that changes it to 1 higher atomic number value. And then we have +0, 1, so that's our electron there. And so positron emission, we have a change in the atomic number of -1. The mass number doesn't change. So there, the Z -1 is the new atomic number, and then that would change it to whatever that element is. And finally, electron capture. Electron capture is a little different than the stuff we've been talking about because it's not emitting something, it's capturing electron from the electron cloud surrounding the nucleus. And so there, it's a change of -1 to that atomic number, but the change is because we're adding an electron there, resulting in the atomic number decreasing by 1. Because remember that atomic number, when it's neutral, is the number of protons or it's the number of electrons. When you start getting it unneutral, then you do some different things there. So once again, this knowing what the changes are in the atomic number or what the change is in the mass number, and the mass is pretty easy because the only one that changes is from the alpha emission. The others don't change it. But the atomic number does change based on which of these processes occur. But we use that information to balance out our nuclear equation. And so once again, I think it's pretty straightforward if you remember what alpha, beta, positron, electron capture, what those represent. And so if you're able to do that, I don't think you'll have a problem. Okay, so let's look a little more detail in these. So when we talk about alpha decay or alpha emission, we're talking about a loss of an alpha particle. And remember that alpha particle is defined as the helium nucleus, 2 protons, 2 neutrons. And so there's our symbol, He, and then the 4 and the 2. And so it's losing that. So in this case, we have U-238, And so if it's losing 4, there's our 4 for the mass number, that puts it down to 234. And it's losing 2 in terms of atomic number. So it goes from 92 to 90. So what you would need to do is you need to look at your periodic table and say, okay, what element is an atomic number of 90? So one thing I'll tell you right now, one thing you're gonna have to do the homework problems or take the exam is you're gonna need a periodic table or a list of the elements so that you can see what the atomic numbers represent. I know for me personally that these nuclear elements, I don't always remember the numbers. I don't always remember the names because you just don't use them that often, except when you do the chapter on nuclear chemistry. And so I wouldn't worry about memorizing that. I would just have your periodic table handy or a list of the elements handy, which gives you the atomic numbers. So in this case, like I said, U-238. So since you're having the emission of the alpha particle, that atomic number goes from 92 to 90. You look that up, you get thorium here, TH. And then to check that it's balanced, you see 234 plus 4, that equals 238. 90 plus 2 in the bottom equals 92. So everything balances. So notice that we don't balance any of the elements. So that's the difference in the balancing here versus what we've been doing before. Before we would have been trying to balance it out so we had the same elements on the left-hand side and the right-hand side of the equation. For this nuclear stuff, we don't do that. What we're worried about balancing are the weights, atomic masses, and then the atomic numbers. So that top number set and then the bottom number set. And so that's what we checked here. And that's what we're going to do for any of these. We're going to understand what's either being emitted or picked up. And then what does that mean? Like I said, with the alpha is the one that's the most significant because you got the 4 and the 2. The others are not as much going on. And the other big thing is if that atomic number changes, and in this case, it went from 92 to 90, it's a different element. So you got to look up that element and see what it is and get that correct. Okay, let's look at beta decay. So we lose a beta particle. And remember, we said beta particle, and people get 2 different ways. Hold on a second here. So this can be written 2 separate ways. The beta can be where you have the beta symbol and then the 0 and the -1, or it can be written as an electron, 0 and -1. Either way, you'll see it written either way. And so what we do here is, started with I-131, because there's no change in atomic mass, we don't have to do anything, so that the top number stays 131, but we have a -1 impacting the atomic number. So if we've got a -1 on the right-hand side emitting, it means that we're going to pick up 1 on whatever this new element is, okay? So in this case, it's 54. So we look up what element is 54 in our periodic table, and we'd see it's xenon. And so now we go and make sure everything balances. The top part is trivial, 131 on the left, 131 and 0 on the right. But on the bottom, this is how we remember that it goes up 1. We had a -1 emission here on the right-hand side. So -1 plus a +54 is 53. and it's 53 on the left-hand side. So we know we've got things balanced there. So once again, the thing you got to get used to on these nuclear equation balancings are that you're going to be changing usually what the element is. And that's the whole nuclear decay thing that we talked about just briefly in the beginning. And so by having these emissions, or in some cases picking stuff up, but having these nuclear changes, you actually are making new elements. And that's the weird thing about nuclear chemistry. We haven't done that at all this semester. Everything else was, as I said before, working with those outer electrons, doing reactions, moving atoms around. But if you think about it, we never changed the atoms. We may have changed the configuration, but we didn't take something, we didn't take iodine and change it to xenon like we did here. So I don't think it's a real hard thing to understand, but it is, at least to me, kind of a weird thing after what you normally talk about in the chemistry stuff. Okay, gamma emission. That's the loss of a gamma ray. And remember, that's that high energy radiation. And it usually accompanies the loss of a nuclear particle. In terms of balancing equations, it doesn't do anything because it has no impact on either the atomic mass or the atomic number. Okay, positron emission. So this is where a positron is emitted in the decay process, and that's a particle that has the same mass but opposite charge to an electron. So remember, the electron had a -1 on the bottom, positron is a +1, and we see here we have carbon, in this case carbon 11, which is a little unusual, but that's fine. We see that no change to the mass, 11, it stays 11, but now we have a +1 down here on the right-hand side in the bottom. So to make our atomic number balance, if it's 6 on the left-hand side, it's got to be 6 on the right-hand side. So if we've got a +1 coming from the positron, then the new element has a value of 5. So once again, we look that up in the periodic table and see that it's boron, and then make sure our balance is on the bottom, 6 on the left, 5 + 1 on the right for 6 on the right. So things would balance there as well with our atomic number. So hopefully you're kind of seeing a theme here. It's kind of the same thing over and over. You got to identify what type of emission or decay is occurring and what that means in terms of impact on atomic number and mass number. And then you need to figure out if that atomic number does change, what's the new element. Okay, electron capture. So this is one that we talked about just a moment ago about how an electron from that electron cloud gets absorbed by the nucleus in this process. And so in this case, we see here on the left-hand side of our equation, an addition of an electron. So there's no mass involved, but there is that -1 in terms of the charge. And so that's going to impact our atomic number. And so here we see, in this case, the rubidium, 81 stays the mass, 37 and -1, we have a new atomic number of 36. And so we would need to look that up to get what the new element is. Okay, any questions on the balancing stuff? So once again, the key is a couple things. One is remembering whether it's alpha, beta, gamma, whatever is happening, what is the impact of the material you're starting with in terms of potential changes in atomic weight, and also atomic mass, but also in terms of the atomic number. Once you figure that out, then you know if you need to add or subtract anything, and then it's a matter of balancing those numbers out on the left-hand and right-hand side of the equation. As I said before, usually that involves that atom, that element changing. And so then once you know what the atomic number is, you can look that up on the periodic table and see what the new one is. Now, if you want to memorize the whole periodic table, that's great, but most people don't do that. They just look it up. Okay, let's talk about nuclear stability a little bit, because we said we have all this stuff happening, and that's why we're balancing the equations. And so any atom that has more than one proton, so the only thing that has one proton is hydrogen, right? So anything besides hydrogen, you have repulsions between the protons in the nucleus. And that kind of makes sense. You know, we always said like charges kind of repulse, opposite charges attract. We've been saying that all year. So that kind of makes sense. There's something called a strong nuclear force, and that helps keep the nucleus together. And the neutrons are the key in stabilizing the nucleus. So that ratio of neutrons to protons is really the key thing that you look at to see if you're going to have nuclear stability. Okay, so you can calculate a neutron to proton ratio. So in other words, we know the mass number, right? That was the one on top. And what did we say that was? We said that was neutrons plus protons. So we know that number. We know how many neutrons are present, right? That's the number on the bottom. So if we subtract the bottom number from the top number, then that would give us the number of neutrons, and then we know the number of protons. So we can use those numbers to have a ratio. So divide number of neutrons by the number of protons, and we get a ratio. Okay, so it's a pretty simple calculation when we think about it in terms of what information we're given in terms of atomic mass being protons plus neutrons, an atomic number representing the number of protons. We can do that subtraction, then do that division, and we get this ratio. And that's what we have plotted here. Okay, so I'd like to spend a few moments talking about what this plot is. So on the x-axis down at the bottom, we have the number of protons. On the y-axis, going from 0 to 160, we have the number of neutrons. So we could go ahead and do that calculation I just described to get that ratio, and then we could plot the stuff, okay? And that's what's been done here. And there's a few things that you see, is that for the smaller nuclei, less than 20, you have a neutron to proton ratio approximately 1 to 1. And that's what we see down here at the very bottom here. So if you go over here to the 20 on the y-axis, you kind of see from 20 on down that it's pretty much on the red line. The red line is 1 to 1 ratio. And we see this bottom part, the very bottom part, it lays on that line. And so we're saying that for the bottom ones, it's right on that line. If it's right along there, those are all pretty stable too, okay? As the nuclei get larger, we need more neutrons to stabilize things. So nuclei get larger, means we have more protons. And so we talked about that repulsion that the protons can have, could cause some problems. And the way that gets balanced is by the neutrons. So you need more neutrons as you get to the bigger nuclei to keep things stable. And so if we look at this plot here, you see two things. One is you see this kind of yellowish thing. We're going to focus on that. And within that yellowish band, the yellowish band is just the ratio numbers, neutron-proton ratio numbers. Within this yellowish band, you see that what looks like dots through there? Those dots, that's what's called the belt of stability, you know? That, I always think that's kind of funny. It seems like it kind of comes out of like a cheesy science fiction thing, belt of stability. And so what the belt of stability says is that things that lie on that are going to be stable, okay? If you get above the belt of stability, okay, then you get a lot of beta emission. If you get below the belt of stability, you can get positive positron emission and electron capture. So in other words, the key is if you're along the black line within that yellow stuff, then things are okay. If you're above it or below it, you got something going on, all right? And what we see is down at the bottom here, at the very bottom, we were pretty much on that line. The belt of stability was overlapping with our 1-to-1 ratio. As we got further along to the bigger nuclei, we see our 1-to-1 line, that red line, really starts to move away from the belt of stability. Belt of stability goes more kind of towards the left. And we see these ratios, we see down here around 30, the ratio is 1.15. We get up to about 75-ish, that ratio is 1.4. We go higher up here at the very top, that ratio is 1.5. So we see that ratio increasing steadily, and that's that bit about bigger nuclei need more neutrons because you got a lot more protons, and you got to try and counteract that proton repulsion stuff. Okay. So once again, if you're above this belt of stability, you got too many neutrons, and they decay, and you emit the beta particles. If you're below it, you have too many protons, and they become more stable then by doing positron emission or electron capture. And you think about it, that makes sense. The protons plus charge, these things are adding negative charge to kind of balance stuff out. But depending upon if you're above or below, it's a different process that's occurring. But what is the same is if you're above or below this belt of stability, something's going to happen, okay? The other thing is nuclei with atomic numbers greater than 84 tend to decay by alpha emission. And so we go back to here, and that's what we see up at the top of here, okay? So we get above 84 and things will just, you have decay occurring. Okay, so one interesting thing about radioactive decay is that it often doesn't just happen once. And so here we have an example here of uranium starting out. And so uranium's radioactive, and so some of these radioactive nuclei have one transition, nuclear transition, but they're still unstable, so they'll continue to have more. And in this one, we see at the top, if it's a red arrow, that's beta emission decay. So we got a couple beta emission decays here. And then the black ones are alpha emissions, and we see that going down. So I don't know what that total is. We got 1, 2, 3, 4, 5, 6. We got like 14, I think, processes going on. And we wind up all the way from uranium up here around over 238. And we wind up all the way down to 206 in terms of mass number. And we're at lead. So that's the other interesting thing is that you went from uranium, which has an atomic number of 92, and wound up 10 atomic numbers lower down at lead there at 82. So there are a couple kind of rules of thumb about the nuclei, is that if you have 2, 8, 20, 28, 50, or 82 protons, you tend to have a stable nuclide. If you have 2, 8, 20, 28, 50, 82, or 126 neutrons, you tend to have a more stable nuclide also. So if either of those occur, those numbers of protons or those numbers of neutrons, you have greater stability. If you have nuclei with an even number of protons and neutrons, that tends to be more stable than ones with odd numbers. So just a couple rules of thumb here. Certain numbers of protons and certain number of neutrons, and that's the values listed here. Those nuclei are usually stable. And then if the protons and neutrons are even, that's more stable than if they're odd. So sometimes people want to cause transitions to occur. So we've been talking about the ones that just kind of occur naturally. But sometimes people want to make them occur, and there's a few ways to do that. So one is called a nuclear transmutation. And you can cause that by having a particle collide with the nucleus. There's something called the particle accelerator. Sometimes you refer to them as atom smashers. And they're really big, and they use magnetic and electric fields to make the particles move really fast, and then they smash into them. There's also something called a linear accelerator, and that's where you have all these tubes of different lengths, and the particles move really fast. I think there's some pictures in your textbook of these. I didn't bother to put them out. These particle accelerators and linear accelerators are just huge, huge things. There's only a handful of them in the world. And so if you want to see the pictures, like I said, I think they're in the book. There's something called a cyclotron, and that uses a D-shaped magnets to keep the particles moving in a spiral. And then a synchrotron does a particle acceleration in a circular way. So basically with these, you get things moving real fast. Some other ways to do transmutations, you can use neutrons. And so the synthetic isotopes that are in medicine are usually prepared by bombarding with neutrons at a particle. And so that's the one, the stuff in medicine is probably the one that you may, hopefully you don't, but you may have some interaction with, because that's used for diagnostic testing and things like that. There's the transuranium elements. So transuranium means the elements right after uranium. And those elements were all discovered by bombarding isotopes with neutrons. That's the thing about some of those elements in that area of the periodic table. You don't find those in nature. They're I don't know if synthetic or man-made is the right term, but that's how some of those were done. And then ones that were higher than atomic number of 110 were made by colliding large atoms with nuclei of light elements with high energy. So once again, kind of made in the lab to generate those, but they're stable, so they get considered to be elements. So there's ways that people write these nuclear equations to represent the transmutations. And at the top here, we have nitrogen and helium reacting together to give us oxygen and hydrogen. And so if you look at this closely, what you're going to see two things is, just as before, we talked about balancing the atomic mass number and the atomic number. So remember, the mass is the one on top, the atomic number is the one on the bottom. So in this case, we see on the left-hand side, we got 14 plus 4 is 18. On the right-hand side, we have 17 and 1, so that's 18, so that's good, that balances. Down at the bottom, we have 7 plus 2, that's 9. And on the right-hand side, we have 8 plus 1, that's 9 also, so that balanced. The other thing I'll say is, sometimes it's written, instead of writing it out with the elements, it's written out with alpha and then P. P stands for proton. And remember, hydrogen is proton. So either way of those, it's done. Down at the bottom here is a shorthand way to do it. And I guess this is what like the real nuclear scientists do, is in this parentheses, they have the alpha here on the left, that signifies the bombarding particle, the nitrogens, the target nucleus. We have the product nucleus, in this case, oxygen, and then we have the ejected particle, which is the proton. So either way of those is acceptable to represent those nuclear transmutations. So probably when people think of, one of the things people think about when they think of nuclear stuff is they think of nuclear decay. And then there's a term in there called half-life that we're going to talk about. And it's that nuclear decay process that you hear about every so often when someone finds something really old and they do what they call carbon dating on it. And carbon dating is taking advantage of understanding that nuclear decay process and what the half-life is of carbon-13 or some other thing, but usually it's carbon-13 decaying. And by doing a nuclear measurement on that and finding out how much carbon-13 is still there, they can estimate how old the thing is. So like the dinosaur bone or whatever it is that they found. And so that's because radioactive decay is a first order process. And so there's our equation for a first order process, which I know everyone remembers because we did that. The kinetic stuff a while back. And if you don't remember it, that's okay. You'll refresh your memory in time for the final. And then that gets us to the equation for half-life. And hope, like I said, once again, hopefully that looks familiar to you. And so for the radionuclide, that is the amount of time required for half the sample to decay, okay? So it's pretty much the same definition when we talked about half-lives before, except now we're talking about it with regards to these radionuclides. And this is a table that I think is kind of neat, is it's got what some of the half-lives are. And let's focus on the natural radioisotopes. We're not going to worry about the synthetic ones, but for the natural ones, so we have uranium, but let's look at carbon. So carbon-14 in this case, 5,700 years is the half-life. So that means if you have something and you let it sit on the table for 5,700 years, half of that carbon-14 will be gone in 5,700 years. And remember, when we talk about half-lives, it's half, half, half. So you technically never get to zero. because it's always half and half and half and on down the line. But we look at some of these, we see like the uranium ones, 4.5 times 10 to the ninth, 7 times 10 to the eighth, one thorium, 1.4 times 10 to the 10th. That's years. That's a lot of years. And so this is why, just focusing on the carbon one though again, this is why using that and these other isotopes, they can measure it, and that's how they get these estimations on how old the really super old stuff is. For the synthetic ones, this would be more likely what you maybe would use in medicine. The iodine one down here, we see 0.022 years. I don't know what that computes to, but I think it's not very long. And so that's where those kind of things are used in the medicine thing, so it doesn't stay in your body forever. You wouldn't want to use, cesium, which stays there for 30 years half-life. That might be a problem. So these half-lives, and then on the right-hand side is the type of decay, either alpha or beta emitter. But to me, the interesting thing is the half-life in years number. Okay, this is what we were talking about before, how they do the dating thing. And this is, as we just saw, carbon 14, 5,700 years. It's limited, you can only do 50,000 years old. Because apparently after that, if it's older than that, there's not enough, the signal's too low. So, and then I guess they have here, they use some other isotopes for rocks. They have a uranium one and a lead one there. So that's what we were talking about, how this is something that I think most people have heard of, especially when someone finds something real old and they try and figure out how old it is. This always comes up periodically, but that's how it is. The last thing I want to just mention is just kind of some of the units that you may hear when people talk about radioactivity. And so when we say radioactivity, what we're talking about is the rate at which the sample decays, okay? And to measure that activity, there's something called a becquerel, and that's 1 disintegration per second. And then there's something called a Curie. The Curie is the one that you tend to hear about more. That's named after Madame Curie, the lady who did all the nuclear radioactive stuff and then won the Nobel Prize and died from it and all that story. I think most people have heard that story. So Curies is what you tend to see it expressed as. And that's 3.7 times 10 to the 10th disintegrations per second. And that represents the rate of decay of 1 gram of radium. So let's talk about nuclear reactions for a few minutes. Nuclei have a lot of energy in them. And this is where Einstein's E equals mc squared, that relates to the calculation of the energy. And so if we look at, just to get a feel for how much energy is there, and the purpose of this isn't so that you learn how to do this calculation. The purpose is just show you there's a lot of energy there. So, so here we have uranium going to thorium, and we do our energy calculation, and it's 1 mole doing that transition with an alpha decay. And you go ahead and do the calculation. And what's interesting is you get minus 4.1 times 10 to the 11th joules, which is 410 billion kilojoules. Okay. The negative sign, as we remember, negative means exothermic. So that means that energy is being given off. So you think of that. Think of how big that number is. And that's for 1 mole. 1 mole is not very much. And so this is why people are always interested in and always have been interested in these nuclear reactions, is the potential energy. So as we'll see in a moment, what goes on in the sun is a bunch of nuclear reactions. Here, we're more familiar with the nuclear energy, which is a different nuclear reaction, actually not as powerful as the ones on the sun, but all of them contain a tremendous amount of power, and that's always been the allure of the nuclear energy field. So where does the energy come from? Masses of nuclei are always less than those of the individual parts. This mass difference is called the mass defect. And the energy needed to separate the nucleus into nucleons is called the nuclear binding energy. And so here's just a table of some binding energy values here on the right-hand side. Some mass defect data there. And this is what is the reason for the big energy in those. So if we go ahead and look at and divide the binding energy by the number of nucleons, that gives us a value that we can then compare things. And so what we see is heavy nuclei gain stability and give off energy when they split into two smaller nuclei, and that's fission. So over here on the right-hand side, we're seeing with these larger ones, that's where fission can occur. Lighter nuclei, over here on the left-hand side, we can combine those, and when you combine those, energy is emitted, and that's fusion. So fission and fusion are the two ways that you can create energy out of the nuclear processes. So if we compare chemical energy and nuclear energy, so remember we talked about chemical energy, we've talked about this all semester, is we're talking about making and breaking bonds, right? That's those electrons, those outer electrons are usually involved in that. Compared, and that's a certain amount of energy. We did a lot of energy calculations, we talked about that. Nuclear energy by comparison is a lot, because we're not just breaking a bond, we're changing an atom. And so that's a big deal. And so because of that we're changing the nucleus, making different atoms, that's the reason by the big energy thing. Okay, so commercial nuclear power plant. So that's fission. And so what did we say fission was? We said that's splitting the atoms, right? And there's different ways you can do that. Here is U35 showing two ways U35 can be split. So if we look there, in this case, it's a neutron bombards it, and that starts the process. So we see here the neutron starts the process, and then it just kind of goes from there, because now you've got neutrons are released in the transmutation, strike other nuclei, causing more decay, and it just kind of propagates itself. And this continuation, that's what's called a chain reaction. So you get it started with those initial neutrons, and then from there, it kind of just does it itself as you have the fission occurring. And here's kind of a cartoon look at it. Okay, the minimum mass that you must have for a chain reaction to be sustained is called the critical mass. If you have more than the critical mass, that's called a supercritical mass, and that's where you get an explosion. And that's how you do the weapons. So basically, you have enough material there so that it kind of goes crazy. Okay, in fusion, you have nuclei of lighter elements are fused together to create heavier elements. So it's kind of going the other way from what we've been talking about. just like with the fission reactions, these fusion products have higher nuclear binding energies, so energy is released. So in both of these processes, energy is released. Fusion has about 10 times more energy per gram than fission. So we see an example of it down here below of fusion, two different types of hydrogens forming helium. And we see in big letters at the end here, a lot of energy comes out. So fusion is what we're talking about with the sun. And it's also become how they do the modern nuclear weapons. So what's the advantage of it? Well, if you could figure out how to handle it, you would basically have unlimited energy. You wouldn't have a bunch of radioactive waste products. And one thing that's interesting is, so deuterium, so that's the heavy water, that's the D, so D2O. So deuterium in water is a reactant. And so you can use that. And there's a lot of that around. Disadvantages, you need high temperatures. And this is the biggie, lack of materials available for containment. Okay, it's kind of hard to do something if you can't keep it in the container. And then currently the production methods use more power than they produce. So in other words, it's not an efficient process. But this is kind of this controlled fusion is kind of the holy grail of energy. Because that's, like I said, that's what's going on in the sun. We know how much energy the sun produces. And if you could just harvest a fraction of that, that would be a big deal. Okay, so when we think about the environment, whether you realize it or not, you're being exposed to radiation constantly. And if you don't believe that, go on the internet and you'll see some of these conspiracy theories about what you're being bombarded and things like that. But part of that is true. But there's two types of radiation, ionizing radiation and non-ionizing radiation. So like radio frequency stuff, that's non-ionizing. What did we say was an ionizing radiation? We said the gamma was, right? So that's why if you think about when you get an X-ray, well, X-ray is not a good example, but if you're doing something with gamma radiation, there's going to be protections involved so that you minimize exposure to that. Most living things, or the bulk of living things, is water. And so if you have ionizing radiation, one of the problems is that you can create what's called free radicals. And so these OH radicals can form, and that's known to cause cell damage. And so this is something that there's a lot of stuff in the literature about this, about free radical formation and how that impacts your health and all that kind of stuff. We're not going to get into that, but if you're interested, you could Google it and see. And it all centers around, you know, if there's different ways those radicals can form. It's not just through ionizing radiation. There's other ways too. But it's that same common theme. And this is why ionizing radiation, that's not a good thing, but don't get it confused with the non-ionizing radiation. Just as we talked about with this nuclear chemistry, those are different reactions than our normal organic reactions that we've talked about because the energy levels are so different. That's the difference on this ionizing and non-ionizing radiation. And that's where sometimes people get confused about that. And then they think, oh my gosh, you know, this radiation from some device or something is going to kill me or cause a problem. Well, it doesn't. It's the wrong energy level. Okay. When we talk about energy doses, there's two ways you hear it measured. Gray is one. The rad is the more common one, I think, that people are familiar with. And as I said before, not all forms of radiation harm tissue equally. And there's actually some relative biological effectiveness, RBE value, that can be generated to tell you, is it really a problem or not? And then finally, you may have heard this term, REM. So that's the effective dose. And so that's how you can kind of do some of these calculations, is using the REM and the RBE value and things like that. So here's some homework problems I would suggest you take a look at. It's mostly balancing equations and things like that, and some questions about the different types of emitters and things like that. That is it for this chapter. Does anyone have any questions? Okay, so just to remind everyone, Thursday, we will have exam 5, which covers chapters 21 and 24, and that'll be online in Canvas. So log on during class period and take the exam. For this section, the final exam is Thursday, May 6th at 8 a.m. So between 8 and 10, the exam will be posted on Canvas. So go online and take that. The length in that will be similar to what an exam is. So that's it for the lecture. I just want to say to everyone, thank you again for taking the class. I enjoyed teaching you. I hope you enjoyed the class. And, you know, keep working hard a little bit here. You got a couple more exams to do, and then you'll be finished. So thanks again.